Thank you very much, Dr. Yang, Dr. Cooks, for inviting me. I'm excited to be here. Our group is working diligently to make it even smaller. And part of the idea is, normally what we do is we take it to an extreme, and we realize that that extreme is implausible, and then we come back to some happy medium. So anyway, we're working hard to have a 1-pound mass spectrometer, but when we have our 1-pound deployable mass spectrometer, it's very limited in its function, so I'm going to talk about that. So Dr. Cooks and Dr. Austin, Dave, all talked today about some of the limitations of where the mass specs, and I'll talk a little bit about that and why we can't go as far as we want to. In the back I do have, the components that we have for the ReMiCIT, if you guys are interested in that and what kind of boards that we're driving. The main board is the electronics board right now in order to drive something this small. You know, the students always love to come up with acronyms, so I always let the students do it. I never come up with good ones. So this is Stephen DeVilla's deployable remote miniature ion trap, and so the idea is to make a mass spec with absolutely no moving parts. If you can make one with no moving parts, then you can make it deployable. If you can make it deployable, you can launch it. You can launch it into a fire, and this idea is right now. But we have to make it small and lightweight. Problem is going to be our pumps, as you guys know. That's going to be the issue. So I show this. Dr. Cooks and I have always shown Dr. Spock on here because the idea is, what does a tricorder look like, right? And so, but I'm showing this for a little bit different reason. I've been recently working with Department of Defense and with Department of Defense and some of the things that they want. If you ever noticed on Star Trek, whenever they need to analyze the planet, they always send the smartest guy down. But for the U.S., we've got to make it red light, green light. If we don't make it red light, green light, then nobody wants to purchase it. So the idea is that miniature mass spec, I have no doubt, is one of the 3 in the tricorder. But the other 2 are yet to be seen, maybe Raman, maybe something else. But we're not sending the smartest person down. Typically, this is something that we have to have a red light, green light type of effect. And so that adds an extra issues. I'm going to shamelessly plug the harsh environment mass spec. As you guys know, anytime we take a mass spec out of the lab, it's in a harsh environment. I don't care if it's 500 pounds or 1 pound. You take it out of the lab, it does not want to be there. And so we have a harsh environment workshop that we do every 2 years. Tim Short, Dr. Hoffman, Dr. Cooks, Wayne Grice, all of them have been very active with this, Dr. Petter. So we've put these mass specs in all kinds of weird and odd places. And so if you're interested in that, that's going to come up in September, and I have some cards in the back. So the idea is to make a deployable mass spec with no moving parts. And the ReMiCIT's down here in the bottom corner here. This is the CAD design that we have for the final product. And the idea is, one of the ideas is if you're in a battlefield, you have you're landing troops in a certain area, the troops are going to go one way. You need this, if anybody's going to do a gas attack, can you drop down some sort of sensors that can detect that and protect the troops from around? The only way to do that is to produce an instrument that can handle the drop. And can we make a mass spectrometer to do it? So again, cylindrical ion trap. Like Dr. Austin said, there are other ways to do it. We have done it. We've even made multi-pass TOFs. Not a bad idea either. Small sectors, which Dr. Hoffman has, which we put on Mars initially. But again, we're going to do a cylindrical ion trap, and this is the best design. So the cylindrical ion trap is actually this small part right here. These are the optics. It's very similar. Ours is a 1 millimeter ion trap based on the original designs when I was working with Dr. Mike Ramsey and Bill Witten at the time. And so the idea then is we've got to get the electronics, the batteries, all of this in there, and the pump. Because as we all know right now, if we want to detect, if we want an ion gain of 10 to the 5 or 10 to the 4 even, we have to have pumping. Without it, we can't do it. So we have to somehow protect. There are ways to ionize at atmospheric pressure. There are ways to run the traps at atmospheric pressure. But there are not ways of detecting at atmospheric pressure right now and getting good sensitivity. And so we have to have pumps in some way. And so I'll talk about how we're using some chemical pumps for that application right now. But this is the device. You'll see it in the back there if you want to. It's actually the small hole dice from the cylindrical ion trap and the electronics board back there. And then this is our little chamber that we've created. Very, very small volume, which I'll talk about in a moment too. So the idea, we've all talked about why we want to make the trap smaller and smaller and what are the benefits, and we all said that there were benefits, so I'm going to kind of show you what those are. So if I take this same 1 centimeter platform and I make it smaller and I array it, But if I use the same area, but then I go an order of magnitude smaller from 1 centimeter to 1 millimeter, 1 millimeter to 1 micron, and to 1/10 of a micron. I use that same area. I get some benefits and I get some drawbacks. The main benefit is that each ion trap holds less ions. But the space charge effects do not flow linearly to the size of the array. And that's the advantage. The advantage is that the space charge effects, even though I can only hold a small, maybe 10 ions in each one of those traps, if I have 100,000 traps, then my gain is still actually starting to increase. So as I go smaller in that same amount of array, I actually get an increase of the number of ions that are ejected. So this is the holy grail. We definitely want to array them. But what's the problem with arraying? And Dr. Cooks talked a little bit about that also. So we tried it. I mean, like, you know, with Mike Ramsey and Bill Wittengrew and Jeremy Moxham, we went all the way to the extreme. So we went to this 40 micron trap that were in silicon manufactured, and we put this array. So we use xenon. Xenon's always a good one. You get a nice isotope distribution. It's beautiful. It won't fragment. You'll always get the same mass spectrum. But when it looks like that, that's not good. And part of the reasons that you see here is, even though technology's gotten better and better, and I'm going to show you when I went to Zyvex and we started doing microfabrication with silicon on insulator, that it's very, very difficult to drill a reproducible hole as you get smaller. 1 millimeter, okay. 100 microns, maybe. After that, very, very difficult to have a reproducible hole. So now, what are the trap conditions for each one of those traps? If they're not exactly the same size, or they have scalloping on their edges and they cause aberrations for each one of those things, they're all going to be individual traps when we're trying to run them at a single frequency with a single volt peak to peak. Can't do it. And this is what you get. You also have alignment issues. You essentially want to use a single detector. It's going to be nice eventually, like Dr. Oxton said, if we had atmospheric pressure detectors that were charge coupled devices, and we wouldn't have a problem at all. We could just align a charge coupled device with this array, and then we would just analyze each trap as it came out and then use the computer software to reconvolute this structure. But we still have a little bit of waste. All of us, if you've noticed, some of us are now electrical engineers that are doing this work. Most of us are chemists that still do it, but we surround ourselves with electrical engineers. And the reason is a lot of these problems that we're dealing with now are high impedance, low impedance, high frequency, becomes a real electrical issue. So when I was at Zyvex, we started to do the silicon on insulator process, and we published this paper back in 2009. And we made some great devices with silicon on insulator. I really like silicon on insulator. It will cause some charging effects, but you can alleviate that by reversing the electrodes. But silicon on insulator works in that we boron dope the silicon so that we metallize it. We metallize it. It's on a little bit of an insulator, and then you got your backside etch. And what you can do is you can do what's called deep reactive ion etching. Again, this is the MEMS technique, but we don't use the MEMS word much anymore because you won't get funded. All right, but the nice thing about making mass spectrometers with MEMS devices is that they're static. And static MEMS is okay. It's dynamic MEMS that gave us MEMS the bad terms because silicon just eats itself. But if you have dynamic packages, then what we can do is we can coat these things with gold, we can isolate them, we can wire bond them, we can do all kinds of stuff. So the first thing that we made was a Bradbury-Nelson gate. So we made a very nice Bradbury-Nelson gate. The first one I made was with wires. That was a mistake. We had to heavily pad that because the electrostatic stiction that occurs when you try to put a charge on there causes the ends to just flop up and ground out, and that's bad. So we added some weight to this, but we made a nice little Bradbury-Nelson gate for a 1 millimeter hole, and we can gate these things at less than 3 volts. And so the next device we made was, again, an RF device, and this is what we call the critter, coaxial ring ion trap. The coaxial ring ion trap, and I show it to you at one of the worst ones because you can actually see alignment issues that you're going to have with a coaxial ring ion trap. We actually got good mass spec data. So, okay, this is toluene again. I am with Dr. Austin, and choosing toluene is a great chemistry to look at. It's easy to get in. It's very easy to get in membrane inlet. But we use this coaxial ring ion trap. And there was a lot of advantages to doing this. If we have this coaxial ring ion trap, we can... The reason we need to do this on silicon on insulator is you're stuck with the size. You can't do deep reactive etching if you want a 1 millimeter hole. because you can't deep reactive etch through 1 millimeter without massive scalloping and a funnel effect. You can't do it. So you have to make these things small, usually about 50 microns. So you're stuck into making a slightly larger trap by doing this coaxial ring ion trap. And it worked well. Some of the things you could do with a coaxial ring ion trap is you could isolate. You could isolate the different pads. You could change essentially the voltage peak to peak on any one, and you could create 2 traps. The aberrations would be a little bit high, and you'd lose resolution, but it's possible. So this is kind of neat in that we can isolate each one of these things, and we can build a 3-dimensional structure on a 2-dimensional pad. So you can do these deep reactive ion etchings, create these structures, and then create a mass spectrometer. Again, we want to make sure that it's droppable. And these things are droppable. This pad that we worked in with when we were at Zyvex can handle a lot of G's to do it. But we went back again to drilling a hole into a sheet metal. That's a lot easier for the initial realm. So here we go. This is the actual device that you guys will get to see. And we have 2 types of inlet systems. One, we have this pulse valve. And I'm going to talk a little bit about pulse valve and why we're going to use pulse valve. If we do direct inject and we have chemical pumps, we've got a problem. Again, and I'm going to talk a little bit about that. And then we have a membrane inlet, and we have a small membrane inlet heated leak here and the chemical pumps. This is a blow-up of the actual device, and this is the one that you'll see in the back. Okay, so just not to put everybody to sleep, but I need to get you some ideas about the way we're going to manipulate the ions in this system. It's very simple. You add a sort of an arbitrary waveform. You can add this with some certain frequency. You mix it. You create the ramp. You increase the ramp and inject the ions. You need to turn your ion source on. You need to turn it off because your detector is on. When you're in a small environment, you don't want electrons flying around your little area, so you have to be able to turn those off. Metastables will just cause your detector to go hog wild, so you have to turn these on. So this is sort of the idea on the signal on how do we make the mass spec in the smaller one, and then pump it right here. So the idea typically also, if we want to also do MS-MS if we can. It's nice that we get, if we can do 1 AMU, even 2 AMU resolution on this device, we still get good peak capacity. But if we can do MS-MS, then we turn that red light, green light device I was telling you about into the less of an orange light. So the one way that we do this is that, we move the ion over to a certain area. We increase the DC potential off to inject the ions off, and then we can bring it back down. Well, again, this causes problems in our electronics. We need to combine all this technology of miniaturing the mass spec, but we also have to miniature the electronics. And by adding a DC to this, it causes our electronics to be a lot larger, especially coupling that to RF. So we want to try to keep it down here on the ground. If I can do that, that would be the way to go. So the idea, essentially, to give you kind of a little model about how this works for any of you guys that are new to this area. We start to trap the ions at a certain potential, RF peak to peak and that. We scan them out, and they scan out in mass order, and that's how we get our mass spectrum, and it's over. So you can create that with an arbitrary waveform and couple it to whatever frequency you want. We want to stay with fixed frequency also. Why? We'd be making a radio if we didn't. And part of the problem with making a radio is turning the coil. If you guys have ever tried this, where you're going to do multiple frequency devices, you need quite a large coil. If I want to make a small electronic board that I can actually make this deployable, I need to make this fixed frequency. So now I'm going to try to do MS-MS with fixed frequency, no resonance ejection on it. And so how do I do it? Well, I play with it a little bit. It's not going to be great MS-MS. We published this in Mass Spec, International Journal of Mass Spectrometry. And we come up and we create our ions here. So now we can actually let the software decide which ion that we're interested in and which one we want to fragment. So when we do that, we push it a little bit on the high bound, push it out. We're on the low bound. Even though the math tells us it won't inject ions on the low bound, there is a hole there. Even though the math tells us there's not a hole there, we lose the ions that are injected when we do this. We keep it isolated. Fragment, and fragment, and then scan the spectrum out, get the parent with the mass. So that's sort of the idea of how we try to do this with microchip controller instead. My next image must be large. Oh, there we go. Whoops. Okay. So doing CID in this type of fashion to isolate the 91 and 92 again. What I did this time is kind of show you that the same amount of time, and if I use that same amount of time and that same amount of energy to create my fragment spectrum, what are my losses and what am I going to actually get out of the mass spectrum? So the idea is that if I'm looking at microvolts for this time period that I'm using to get my 91 and 92, I get somewhere around 80 millivolts of signal for this. If I isolate it and in the same amount of time look at the amount of signal that I get on my fragment spectrum, I'm down to 25. This is another problem. So time is great. It's on our side. Time would always be on our side for small devices, and the reason that we use traps is that we can actually increase resolution based on time and not length. But again, sometimes we need to know a response faster than that. And so in the same amount of time for us to create 80 millivolts of signal on our parent ion, we can only create 25 microvolts in our fragment spectra. But we can still do MS-MS with our simplistic effect, even though we have huge amount of losses. So the idea is now, can we do all this in the MEMS world? Yes. We've got MEMS microvalve thermal inlets, MEMS actuators for pressure regulators that we have now, MEMS mass spectrometers, micropirani gauges, and MEMS source field ionization. So it is possible now to make a deployable mass spectrometer, but it's going to be limited in function. But if in the case of a deployable mass spectrometer, we're looking at things that are in the air anyway. So typically, the idea is, can you launch this in a fire while the fire's burning in an industrial fire, know what's burning in that fire, put it on the battlefield? You're going to have a limited resources. It would be nice to be able to put a benchtop mass spectrometer, as everybody else is shown in here, into the field, but right now it's not plausible. And again, somebody solves the detector problem, we'll be moving. Okay, so the pump. Let's talk about the chemical pump a little bit. This was a lemon lemonade issue. We're using SAS Getters pumps right now, and we're using the ST172. The ST172, if you look it up, is not being used as a pump. It's a hydrogen generator. This is the specific functionality of this. But we were thinking about how to create a buffer gas. And this was coming with Dave Rafferty had talked about already, the space problem. We wanted hydrogen to be the buffer gas. If hydrogen is the buffer gas, NASA's not going to let us ship that compressed hydrogen. So how do you do it? Well, you take a Getter pill. Getter is actually reversible for hydrogen, even though it's not reversible for anything else. So it'll actually extract the hydrogen, and then as you heat it, you can release it. So if you can make small adjustments in the heat of the Getter pump, you can actually control the amount of hydrogen that you produce, and hence control background gas. So that was the idea for this, and that seemingly worked pretty well. But what we found was once we conditioned the 172, it would pump at atmospheric pressure. I mean at atmospheric temperatures, at room temperature. So most Getters that we have are great pumps. They will make our instruments smaller, but we have to heat them in order to run them. And in order to heat them to run them, it's going to cause a lot of wattage. Already we have a light bulb in there that's ionizing, right? We have an electron impact source of some sort, even though they've come up with very nice ones nowadays. They're still pretty isotropic sources, so we'd like to get rid of those. So this 172 actually ran on a membrane inlet leak for 18 hours. And I'll show you that data in a moment. So we were very excited about this, this 172. The test chamber that we had is 3 cubic inches, so it's small. So the mini mass spec chamber, if we had the blank chamber in there, but when we have the mini mass spec in there, it's 2.7. And that's still a lot of empty space that we don't need. We have part of a problem if we run it at 500 volts peak to peak. We don't want breakdown all over the place, so we've got to make it somewhat of a large volume and to put our sample in there. But we can keep these relatively small. So we're at 2.7 cubic inches in the total size of the evacuated area. Our gas load with that membrane inlet is about 4.57 10 to the minus 5 torr seconds on that inlet. So with this type of gas load and with this size of chamber, we can actually get to 172. So we're a little discouraged initially when we did it. So we're at 10 to the minus 5. We pump the system down. We heat it up. this is in hours. We get 10 to the minus 5. We're at 10 to the minus 4 torr. This is where we want to be in order to keep our detector running at about 800 to 1,000 volts in order to detect our signal. So we don't want to really go above this right now. And as the technology starts to get better, that'll be great as we can go to millitorr range. But right now, this is what we're interested in. And this did not last very long. It only lasted about 5 hours. But then we reconditioned the pump. And as you recondition the pump, you start to bury all the atmospheric gases over and over again. And now we're at 15 hours after the third activation. And after the fifth activation of the pump, we're at 18 hours. And to today, so this is 3 years, and to today, we're still running the pump at 18 hours. Now, we don't run it like we would run it in the field. We're not activating it twice or 3 times a day. We may be activating it once a month. But we've probably gone through about 100 cycles, and we're still getting 18 hours of life on the getter with a membrane inlet leak. And so that's exciting on this 172. The other nice thing about it is that your volume area and your surface area don't have to be the same. So the surface area of these pumps, even though SAS Getter typically makes these just as these pills right now, the idea is if you could powderize this, which they would if there was an interest for it, but if you could make a powder out of this, put it in and make a little absorption pump, you get a huge amount of surface area, and hopefully we can lengthen the size of this. Now, if we've gotten rid of the pumps, we've gotten rid of over 30 watts of power, no heater. That's greatly increases our battery life that we have currently. So the idea is that here we have this Pittcon valve, which I'm going to talk about in a moment too. This is another neat leap in technology. But we have these getter pumps here to protect them. These getter pumps would have to be reconditioned more often, of course, if we had a leak, but maybe there was a way that we could use getter pumps even to make the system smaller to protect the detector. So if we had even if we just had a small conductance limit here and used the getter pumps on the detector side, maybe we could run this part under rough vacuum with just a diaphragm pump, and then you keep our detector under a higher vacuum. And so those are the things that we're working on now. These are just sort of those ideas for those ion traps. Okay, the membrane inlet. Oh, the microvalve. Sorry, I pointed to the wrong thing. So let's talk about Pittcon's microvalve. So this is another thing that we were testing for another reason, and it ended up working out. This is actually a liquid spray. Pittcon makes these valves. They have a sapphire ball with a small spring in it. It's a completely mechanical valve, very small mechanical valve. You can make these sapphire and ruby valves very small. You can actuate this, and it will inject a designated amount of liquid spray into your well plates for all of this high throughput LC combinatorial type of chemistry. Well, I said to one of the students, stick it in the vacuum and see if you can still open the valve if you have a negative pressure on the other side. And you can, and it works very well, and it runs for a long period of time. It runs on low current. So you can these are the 2 tag points that you do it, and it's got this small valve that opens and closes in there, and you can introduce a leak. So the idea is DAPI has done some incredible things as far as being able to do external ionization. I don't know yet. We haven't tried to whether the sapphire ball will cause any effect if we can actually ionize on this side of it and continue to keep the ions on the other side of the valve. We haven't tried it yet. It would be a great idea, but right now we're interested more in how do we get atmospheric sampling into it without causing those getter pumps, chemical pumps, or any pump to be able to control that leak. Well, the idea is then, what if you had 2 of them? And one of them was used to just continually. This is the funny thing about atmospheric pressure chemical ionization on mass spectrometers. If you've ever noticed, nothing shuts the valve on the front of an ESI. It's constantly ionizing. And for what reason? The ion trap can only look at a small amount of ions that it's put in there, and then it has to eject all the rest. So it's injecting over 95% of all of the ions that are coming in there and only trapping less than 5% of it. What if I ran the tech valve so that it only opened when I needed it to open and closed when it didn't? So the idea is, here you have this constant vent, this flow. You can add a GC to this if you wanted to. So you have this constant flow on this. And when you need the microvalve, you just open it up. And the only dead volume that you have is right here. as close as you get to that valve. You want to decrease the amount of dead volume too, because you don't want the mass spec to have a memory effect. You want it to be able to clear that as fast as you can. So if you double these micro valves together and put those in there. So we tried it. We did it on the Polaris here system right here. We did it. We stuck the GC. We took the whole GC interface out and just ran it on our Tech-along valves with the helium background. And when we did that, it works brilliantly. You get great mass spectrometers. Here's the valve. When you shut the valve off, it goes straight back down to zero. Very short period of time, and you don't have much dead volume. So these double valves work pretty well. The sapphire balls are kind of nice. Right now, we haven't found any chemistry that's interacting with them and sticking around, but I'm sure somebody can find me a lipid that'll stick there forever. So I'm just going to show you an application that we've done with this small system. And this is an oil and gas well. So this is a problem that we have in Texas. You guys know in Texas, we're drilling wells everywhere. I live on the Barnett Shale. My land is part of the lease. But part of the idea is, are there any B-Texas or any of that type of stuff that's being emitted? It's a very, very costly process. In fact, it's so costly, I think it's $100,000 to get your site tested that most people have just canceled the contracts. It's just too expensive to get them in these neighborhoods. So we're sitting on a lot of Barnett Shale. We're sitting on a lot of oil gas. But we have no mechanism of being able to determine whether these B-Texas are being emitted in the usable amounts. This is my neighborhood. So my neighborhood's, I sit on the Barnett Shale, which is right here, the really dark blue region. So I want it to be safe because it's worth a lot of money to me. I definitely want them to drill below my land, but I don't want it at the cost of my neighborhood. So this is what neighborhoods look like in Texas now. I mean, you can go to Fort Worth in these areas and you'll see these huge drill lines. And so if a child is born with autism or has some sort of birth defects, you know immediately what's going to get the greatest concern is the fact that you have this huge oil rig tower that's sitting in the middle of it. And so we've pulled back a lot on this. So for both sides, for the health side and for the drilling side, we need to know what's coming out of the ground, and we need to know when it's coming out of the ground. So this is a good application for that. These are the B-Texas, right? They're the benzenes. We don't want them because they combust incompletely. They poison the well, and they hurt the environment around it. And so these are the OSHA allowable limits of each one of these types of compounds. So currently right now, here's a tower. Look how high it sits above the surface. This is where the detection is being done right now spectroscopically. They're not going to tell anything. The diffusion is incredible at that point. I don't know if you've been into Texas. You guys landed in DFW Airport. The wind is never friendly. And so being able to detect any usable amount of data spectroscopically at this level is impossible. You need a ground level detector, and you need one that can look at these compounds in B-Texas. So we did current monitoring on that. This is just sort of a scale up on the membrane inlet. We tried different types of membrane inlets. Tim Short's group has done this. Dr. Cook's group has done any of these outer ones. This is the inner loop coming out of the vacuum is by far the best. Orders of magnitude, it clears quicker. This is the best design for our system. And so if we're looking at just acetonitrile in here to show you on that specific detector, as we turn the time on, it goes off. You can see that it's not the membrane inlet is not a concentration-dependent problem. As we go up, it goes down. It's a release time. On the vacuum side, it actually works just as well depending on whether the concentration is high or low. And that's good. We don't want any memory. If the concentration went high and we got this long tail off, we wouldn't want that. So these are the comparison of the three geometries. Again, the coil through flow is by far the best right here as far as sensitivity goes. And it also is the best as far as clearing. Clears at the quickest amount of time with high concentration load, 200 seconds. So we started with just a Faraday cup detector, 3.4 ppm on the signal. We had a channeltron detector, and we get about 165 part per billion, which is well below the limit that Texas needs to know on the OSHA emission cycles. So we started looking at benzenes, hexanes. This is very interesting. The membrane inlet doesn't work well on hexanes, thank goodness, because if we're looking at oil and gas and we're starting to detect on hexanes, that's all we'd see. We wouldn't be able to see the unsaturated hydrocarbons, but luckily the membrane likes the unsaturated hydrocarbons. So we've got hexane and heptane here, and we just see noise. Where with xylene and benzene, we get a good response. And so we looked at Missouri Gold. And these are oil samples that we've been doing some contracts with, pit samples and wellhead sludges. And they're all very nice, very clean, good oil samples. The tar sands, which is phenomenal. This is a great place to get oil. And hopefully there's not a lot of people who live on the edge of the tar sand, because the tar sands do emit a lot of xylenes. Not that you can do much about that, but the tar sand samples are very heavy in unsaturated hydrocarbons. And so we need to know. Anyway. All this work is done with the students, Department of Defense contracting, First Detect with the Emerging Technology Fund, and as Dave said before, with the DITRA. All of this work can't be done with our funding agencies and with my students. They do all the work. I just get the glory. So anyway, I appreciate you guys' time. And if you guys want to see, I'm not going to, the device isn't running, but if you want to see the components of the device and how each one of those are assembled, I have it back there on the electrical board. To show you how we've miniaturized those components.
I got one question. So for that unit, how many, what is the number of units, ST-172, you actually put it in there?
I have 3 of those units. So those units are 9.5 centimeters in diameter and about 7 centimeters tall. And they're completely circular and hollowed in the center. So I have a surface area of both the outside and the inside. That was the best surface area that I could get for the 172. Again, SES makes them as hydrogen producing getters, so they don't have the idea of using that one specifically as pumps. It doesn't last as long as a normal heated pump would if you're going to use it as a sorbent medium. But the fact that it runs at ambient temperature and pumps at ambient temperature for that amount of time is the benefit that you get from that. So that surface area with 3 of those is almost equivalent to the surface area that I actually have of my actual chamber. And we can increase that quite a bit.
My question, Guido, is about the display. So you've got a miniaturized mass-spec in a baseball size, or maybe a bit bigger, and you use it on a battlefield or something like that. How do you display the information? How do you do that?
So, yes, thank you. So, Dr. Chen's group in electrical engineering with us has come up with a way where he takes one of the spheres and he uses that as a remote receiving device. And the rest of them send the signal. So he's created one right now that will run within 100 yards. If each device is within 100 yards of each other, 10 devices can all communicate to one central hub, and then that one can use 4G to send the signal back.
And that's done? Or on the way?
Right. He's developed the chip, and that technology is there. Implementing it for our data is the next stage, yes, sir. Again, surrounding ourselves by good EEs, like Dr. Taylor.
You mentioned the gas load. You were able to handle gas load of 4 times 10 minus 5, and you put torque per second, but it should be torque volume per second. So that's volume of your chamber.
Well, it's already a fixed volume, so our chamber's already fixed volume at about 3 inches squared.
So then the gas load, the gas throughput would
It includes the 3-inch cube. Yes, sir. Mm-hmm. Yes, sir. Yeah, thank you.
Well, if we don't have any more